Não?
Tá.
Não? Mas vais deixar aí?
Consegues? Sim, tento ficar aqui.
Queres uma cadeira?
Não, fica aqui no top.
Okay, I think we're ready.
All right, so we're going to open this workshop with the first session, hydro research, and we have 4 talks, and then there will be many interesting topics, subtopics that will be followed in the remaining of the workshop. And our first speaker is Dave Gartnes, and Dave is from NCAR. And the title of his talk today is Exploring the Gross Soil Moisture Feedbacks in the North American monsoon region.
Did you say there's a way to advance the slides?
That's on there.
It's on there. No, there it is. Okay. Well, thank you, everybody. Good morning. I'm going to talk about some of the work we've been doing with folks at Arizona State University, soil moisture feedbacks in the North American monsoon this session. And Julie brought me into this a little late, so this was some work that we'd been doing, which was relatively fresh and new aspects in this area. For those of you who know let me see if I get this straight. There we go. The North American monsoon area, it is a smaller version of monsoons that we have around the world, where there's a very distinct seasonal shift in the climate circulation, the regional wind patterns, the moisture flux patterns, and therefore precipitation regimes. Normally, this area that we're talking about, which exists in the northwestern part of Mexico and the southwestern part of the United States, is typically very semi-arid. It's hot, it's dry for most of the year. And then the circulation changes in late June and July, and a lot of tropical moisture comes into the region. The deep convection in the area. Convection in this region is terrain driven. So already background forcing mechanisms for initiating convection. And one of the biggest processes we see when it does rainfall is this relationship across terrain gradients about where storms trigger, where they tend to experience upscale growth and propagation. So this is building on many sort of years of research on the background rainfall seasonality structure and its relationship to terrain and synoptic scale patterns in North America. Really tries to illustrate the diurnal cycle in this particular region. And you would see similar diurnal cycle vegetation in many other places throughout the world. That happens early over the highest terrain. Oftentimes that's shallow convection. Some of it persists and grows into actual precipitating storms. Some of it does not. And then later in are off the crest of the mountain chain, and some will undergo deeper growth and organization. In this particular region, there's a very significant interaction with strong moisture that exists at lower elevations coming in from the Gulf of California in western Mexico. And the ones that do happen to make it much less frequently do happen to be very intense. They form mesoscale convective systems, and those can then propagate for many more hours, even out across the open water. So this pattern is fairly well established. You see this stuff almost every day. You see these kinds of events happening maybe once or twice a week in this area. And so our goal was not to sort of recast that particular idea, but look at what are some of the other land surface controls on convective initiation in this particular region. So we had a few fundamental questions that we started exploring in this project. The one that I'll be talking about today is how do changes in soil moisture impact land atmosphere exchanges in the North American monsoon region. Basically, how do soil moisture anomalies feed back to the atmosphere in this region? And then there's a second set of questions, which will be gotten into in later time as the research progresses, which looks at how our representation of land surface hydrology, and particularly how terrain influences the organizational patterns of soil moisture states and sensible and latent heat fluxes, feeds back to the atmosphere. And really answering this question as we get to higher and higher resolution models, is there a detectable difference from a numerical weather prediction or a quantitative precipitation forecasting perspective? So there's a lot of interesting things that are queued up to do here, but today I'll really only be talking about this background coupling behavior. So the outline for the talk is basically this. I'm going to talk a little bit about some of the principles here of hydrometeorological processes related to that question. I'll briefly describe this warp hydro modeling system that we've been using to do this research, and then discuss the results from an uncoupled deployment of the model to get the land surface hydrology set up, and then the results of the fully coupled experiment after that. Okay, so most folks here, I think, have a pretty good understanding of what terrain-driven, thermally driven circulations are and complex terrain. This is a depiction that comes from a textbook by Dave Whiteman and Zardi in 2012, and basically looks at how convective circulations over complex terrain set up at a variety of different scales. This is actually a region in Colorado that they use for this illustration, showing during the daytime upslope flows and then some of the recirculating arms of those flows as a result of the heating of the terrain. These diagrams on the right are just sort of what some of the profiles of near-surface winds, temperature, and turbulent kinetic energy start to look like, either during the daytime in upslope conditions or during the nighttime in downsloping conditions. So if you look at those thermally driven circulations, they're all, of course, keyed to the energy partitioning that happens at the surface. And this is what we'll be talking about most of the results that are presenting today. Typical schematic here of how energy and moisture gets partitioned during the boundary layer and at the land surface during the daytime. Basic formulation of the energy budget equation, net radiation, ground heat flux, energy storage, advected energy into the system, and sensible and latent heat fluxes here. One of the aspects we look at a lot related to what's available for energy at the surface is, of course, how much of the shortwave radiation is being absorbed by the land surface versus reflected off. And that's ends up being quite a significant issue in the monsoon region as well. So these energy partitioning start to couple into the circulation equations here. This is basically the tendency equation for sensible heat production through this term, and this feeds back into the terms which drive circulations across the sloping surface through those two terms there, either through local pressure perturbation or through the gravitational terms. And as you get more sensible heat production, it tends to drive those upslope flows, and at nighttime that reverses as you get essentially a negative heat flux coming into the region due to radiative cooling. So the thing that's important here, of course, is if you go back to this slide, is this balance then. We have this trade-off between sensible and latent heat flux. And really understanding if it's the sensible heat flux which is driving this, a lot of the strength of the terrain-driven circulations, what happens when we get soil moisture anomalies that start to influence the latent heat flux? In this region, is that going to produce a positive feedback, or is it going to produce a negative feedback? The positive feedback would suggest that the moisture is acting in some way, either as a source precipitation or other modifications to boundary layer structure and energetics, which help drive convection. Or is it the other way around, where you need a deficit of that moisture to really drive the sensible heating of the terrain to drive and invigorate these circulations? So there's some subtle trade-offs that we're really starting to look into as it relates to the feedback from soil moisture back to the atmosphere in this region. And this complex terrain circulation is just a big complicating factor on top of the regular energy partitioning at the land surface. Okay. So to explore this set of questions. We're using the Wharf Hydro modeling system. This was actually one of the reasons that the system was developed, was to more explore these kinds of questions. The system's evolved into a sort of a different operational hydrologic forecasting system these days. But originally it was really targeted at looking at land-atmosphere coupling behavior and being able to couple land surface models with enhanced hydrologic process representation into higher resolution atmospheric models. And that's how it got its name. We built this architecture to couple into the WRF model to do regional high resolution atmospheric predictions, but with this enhanced hydrologic capability. So there'll be a couple of talks on WRF hydro in general later. We'll talk about it in its operational deployment as the water model for the United States later. But basically the system is configured like this. We have traditional components of land surface column models, which handle the vertical process physics, canopy processes, snowpack processes, where they're relevant, soil column processes. And then there's a two-way coupling across a multi-grid framework to go from the vertical processes to the horizontal routing processes. Oftentimes, when we're running in a fully coupled mode, the column land surface hydrology is run at the same scale as the atmospheric model, and then the terrain routing processes are run at a much higher resolution. The reason for that is most of the high resolution atmospheric models we're running these days still have resolutions on the scale of kilometers, a few kilometers, maybe 3 kilometers, maybe a little bit higher. And really to effectively resolve terrain slopes, which provide the energy forcing for moving water around on top of the land surface and through the subsurface, we need to be much higher resolution to resolve those terrain slopes, really down at tens to hundreds of meters of scale. So for the WRF hydro system, is that a warning already?
No,
Okay.
it meant nothing.
It meant nothing? It was pretty. Anyway, so the idea here is that we needed to be able to dynamically link these models operating at different scales. And so that's part of the infrastructure behind WRF hydro is to be able to do that. So there's two-way coupling here between soil moisture states and how much water is ponding on the surface, as well as aquifer process, some shallow aquifer processes here. Then, of course, completing the problem is linking to channel processes, and here we have, depending on how you configure the model, either one-way or two-way coupling to river channel flows. River channel flows, of course, are an even separate scale of process than what we're talking about here. Essentially, river channels, or most river channels, except for the largest one, they're unresolved at the atmospheric model scales. You can get some depictions of them at the sort of tens to hundreds of meter scales, but oftentimes you need much higher resolution frameworks for representing channels. And so, again, the WRF hydro modeling system provides frameworks to link to different representations of channel models, whether you want to do them as sort of vector objects or very high resolution grid cells as well. So that's a little bit on the background here that provides us a capability to explore some of these high resolution hydrologic processes and of course how they link back up to the atmosphere. Related to this point then is looking at how these hill slopes then, or if you go across larger mountain chains like we see in places like western Mexico, the southwestern United States, looking at how these processes on complex terrain influence the patterns of soil moisture and sensible and latent heat fluxes. So this is a snapshot. It actually comes from Germany with some different folks who've been using the modeling system. Just as an example here to say when you run these models over long periods of time, you start to develop patterns of heterogeneity in land surface hydrology that you wouldn't get with just a normal one-dimensional vertical model. In this particular instance, this is terrain in this panel at 100 meters. This is southern Germany. This is actually into Austria with the In-River Valley. And this region here is which is the highest mountain in Germany, and Garmisch-Partenkirchen in that area. So they're looking at the alpine front here. A long-term simulation, you see that there's very shallow groundwater as depicted by the dark blue colors here. And then you go up into the mountains and of course the water is drained off into the valley. So you start to get very clear representation of where the valleys are and how that influences the shallowness of the groundwater. Soil moisture tends to organize across those gradients as well, although it can be a little more complicated at the near surface. and then of course relating to stream channel flows. So it's this sort of background hydrologic organization that we're looking for as we move to these integrated hydrologic models. Okay, so back to the monsoon problem. What did we do in this particular study to explore the impacts of soil moisture on atmospheric coupling and convective precipitation? Well, the first thing we did is we set up the uncoupled model, and by that I just mean the land surface model only. And this is when we start to look at things like numerical weather prediction and a lot of different kinds of regional climate modeling. Probably doesn't get done enough of is how people set up and calibrate their land surface component to study these kinds of questions before they go into fully coupled mode. So we did spend quite a bit of time using a number of different research data sets that have been collected in Northwest Mexico over basically the last 12 years now to calibrate and evaluate this uncoupled implementation, really asking ourselves, are we faithfully reproducing the hydrologic and ecohydrologic processes in those areas? The folks at Arizona State are doing a lot of work on vegetation modeling as well, so that wraps into this, although I don't have time to talk about it today. So after that, we're basically trying to establish the fidelity versus these observations. I'm going to focus really on showing some data from some flux towers, as well as some comparisons against MODIS, which is a satellite-derived estimate of land surface temperature and evapotranspiration. From MODIS, land surface temperature is a bit closer to a direct observable coming from the satellite. The evapotranspiration product from MODIS is not an observable. It is very much a derived product. It has its own model that they use within that. So it is a reference, but I wouldn't call it truth in this case. So once we've done that, then we start to do the coupled model experiments, and I'll talk how we set those up, and really just look at the sensitivity to some of the lower atmospheric structure to how we go initialize the land surface hydrology. So here's the region we're looking at. This is Northwest Mexico. The Gulf of California is in this region. Arizona and the United States here, and this is the Mexican state of Sonora. We're working largely in this river basin here, which is the Rio Sonora, that provides water for the city of Hermosillo in Northwest Mexico. This is a blow-up then of elevation, soils, and vegetation, which come from Mexican federal agencies. And these dots that you see are different combinations of local meteorological stations, local soil moisture observations, as well as some flux towers, which is largely the flux towers where the white triangle is in that area. So that's most of the data that we're going to be using for some evaluation here. Okay, so jumping into some of the results. What I'm showing here then is just the tower scale, one-dimensional implementation of NOAA-NP. So we're at a tower site, which is fairly flat. And we start with the most simple case of evaluating how the NOAA-NP land surface model is performing at that particular site. We're looking here largely at latent heat flux in this panel, sensible heat flux in this panel, and comparing them with observations. The model's in gray and the observations are in black. This is a whole season worth of data from 2004, so it's a little hard to reference that. A little easier if you start to look at these in a scatter plot to see what the biases are. Bit more scatter and sensible heat flux than you do in latent heat flux. That's not unusual because it's very hard to measure nighttime sensible heat fluxes. So you do tend to get a lot more dispersion in comparing models versus observations, largely due to nighttime processes. But overall, the model's tracking the observations pretty well. This is a compiled diurnal cycle of precipitation, or of the sensible and latent heat fluxes. So the sensible heat flux here and the latent heat flux here. The model does tend to have a little bit of a high bias at this site when looking at the latent heat flux. But very much within the bounds, the model, which has a much narrower range of behavior, is very much within the bounds of the scatter of the observations. Soil moisture. This is basically just a number of different plots, sites, soil moisture. And we're looking at time series of the one-dimensional land surface model, the fully integrated warp hydro system, but at that point, and then the soil moisture at that point. This is a pretty difficult metric to hit for those who've done validations with soil moisture. This is a point measurement of soil moisture compared with a model grid, but overall you can see in the scatter plots pretty reasonable performance. The time series do tend to track pretty well. If there's one pathological behavior, I would say, it's that in the War Hydro system, as opposed to the 1D model, we do tend to have a much slower recession in soil moisture at some of these sites, though not all. This would be an example where the dotted line is the War Hydro soil moisture. The solid line is the one-dimensional NOAA MP soil moisture, and of course the dots are the observations. And in this case, it takes the War Hydro system a while to dry down after events. Now these changes are still all on the pretty dry end of things, so it's tough to say how significant they are. But you go to a different site, you see different behavior where the model tends to dry out a little bit sooner. So there's some trade-offs in this, but overall the correlation, which is what we're after here, appears to be pretty good, and it doesn't appear to be a really gross overall bias from either the one-dimensional or the fully integrated War Hydro system. Last bit of evaluation then for the offline model is to start to compare what the model's doing versus these ET products. Yes?
I'm just going to remind you, you have 3 more minutes.
3 more minutes? Okay. I'll get through. There's not a whole lot more. So to get to the point here, land surface temperature. This is basically before the rains come on, so we have a very large range in diurnal temperature, and then it starts to narrow down because the system gets wetter and you get smaller ranges in diurnal temperature, both coming from, this is from the model. From ET, we tend to be a little bit high compared to the MODIS-derived ET product, as indicated here. These are, again, days of the season, dry season, wet season, once the monsoon rains onset. The spatial patterns is really what we're after here, so I'll cut to the chase with this and say that this is the spatial pattern of land surface temperature from the War Hydro model and the MODIS remotely sensed product. These are after the rains have onset. This is 2004, this is 2013, and this is before the rains have onset. So you see this big change that happens in the structure of the variability after the rains come on. Beforehand, everything's hot, everything's dry at all elevations and all sort of vegetation types, and you get a lot more variability in these as once the rains come. Okay, so then to move quickly to the coupled model aspects, this is the obligatory slide on the whole WRF model setup, the physics packages and everything that was here. There's really not a whole lot to dive into. I'll just say that this is if you want to look at this later, it's got our mixed grid setup of the WRF Hydro system. We're going to be looking intensively at a couple of different rainy periods in 2004 and 2013 and compiling those together. That's where those gray bars are. And the one thing that does pop out, there's a background analysis of precipitation. This is accumulated precipitation over the seasons. And then there's what the fully coupled WRF Hydro model does. This, the atmospheric model here, WRF and WRF Hydro together, produce precipitation that's a little bit less than what was observed, but with very different structure and a much more episodic structure in terms of heavy rainfall events versus the analysis product here, which is smoothed out quite a bit. Of course, that can have some hydrologic impacts. For soil moisture, you see a lot more variability in the blue there, which is coming from the model versus those background analyses. Okay, so we're going to be contrasting 2 experiments. One's sort of a uniform soil initialization for those rainy periods, and then there is a sort of a pulsed rain event which gets put on there, and I'm going to contrast that with a background simulation, which is sort of a whole season continuously running simulation. And the point here is to say, when we do these initializations, which have more moisture in them than the background simulation, what is the feedback part of that? And then a little bit of teasing out between, is there a really significant difference between the 2 experiments? Number of different analysis metrics I'm going to talk about. The precipitation differences look like this, and I'm showing the sort of the end result first, and we're going to get into a little bit of why. Both the experiments with the wetter precipitation or the wetter soil initializations, regardless if it's uniform or whether it's sort of a more spun up case, tend to produce quite a bit more precipitation in the baseline case. So we're seeing evidence of positive feedback between soil moisture and precipitation in this region. Of course, the question is why. It's not always the case that a wet soil initialization will give you a positive feedback with precipitation. And really the answer lies in some of the lower atmospheric thermodynamics as much as we have been able to tease out. We're using the coupling framework that was proposed by Delta here in 1998 and looking at changes in available energy as functions of soil moisture. And this is actually changes in albedo here. As soil moisture goes up, the albedo in this system tends to go down quite significantly due to changes in soil color with wet soils and also due to increases in greenness. As we get more wet soils, we tend to get more greenness in the vegetation down there, which responds very vigorously to available moisture, and overall albedo starts to go down. Evaporative fraction, it tends to go up with soil moisture, and the midday skin temperature tends to go down with the evaporative fraction. This change in albedo is really your first signature that there's going to be more net available energy in the system because of that lack of reflected energy. Also related to this, we're looking at wet bulb temperature changes and the x-axis here, and midday cake production and midday lifting condensation levels. And so the story here is that as it gets more humid as a result of wetter soils, more evapotranspiration, you tend to get an increase in CAPE in this particular region, and you tend to get a decrease in your lifted condensation level. These are maps of CAPE, and basically if you do the averaging here, everything in yellow, which is a positive increase in CAPE in both of those experiments over the background, tend to suggest that there's more CAPE in the system. Okay, so we know that CAPE helps drive the triggering for atmospheric convection. And it is basically what we're finding is that overall, as we see this changes in the surface energy partitioning, it leads to an increased production in CAPE. And that is what we believe in this case is leading to more rainfall despite the complexity of the surface initializations. So it suggests that there is already sufficient energy to drive convective dynamics in this region, unlike other areas which can be very moist and there's not enough energy to really drive convective initiation. In the southwestern part of North America, there is. It's very hot, very direct sunlight at this time of year, and the system tends to be more moisture limited, right? And so the increase in soil moisture does provide somewhat of a local source, although it's not usually enough to sustain precipitation, but it provides enough moist energy, moist static energy, which goes into the system, which helps sustain and initiate more convection. So there's a whole feedback decision tree framework, if you follow the ELTA here, framework for doing this that you can look at. The decrease in albedo, increases in net radiation, increases wet bulb temperature, increases CAPE, lowers the boundary layer height, and lowers the lifted condensation level. So with that, wrapping up, these studies, along with some earlier, more simplistic studies, have really begun to show that in this region, the North American monsoon, that precipitation has positive feedback with soil moisture anomalies in this area. And then the next steps is really to explore the role as does the terrain routing process really provide an extra imprint on driving the convective dynamics. So with that, sorry I went a couple minutes over.
Thank you.
Questions? Great. In your area, there's a little bit more feedback too, right?
Yes, but on loading range simulations. Can I make a question?
Yes.
Yeah, go ahead.
You talk about your final simulations wetter than NOAA in 1D simulations.
Yeah.
With the observed input, I suppose.
Yeah.
Could it be just a matter of calibration?
Definitely.
Because we discovered that your fiber can retain more water in the soil, at least in our experiments. So maybe.
Right. Yeah. No, I think you're exactly right. It came up in your work, and we see it here. The unfortunate thing is in this area of northwest Mexico, there's not a lot of stream flow data to calibrate the overall water budget too. Otherwise, I think that's something when we went through this, we really wanted to do. You can basically constrain the overall water budget by calibrating the stream flow, but at a local site, it's really hard to do that kind of calibration.
Any more questions for Dave? Yeah.
So do you run a dynamic vegetation model in the system?
Yeah, I had to skip over all the vegetation stuff. That's what the Arizona State folks are really interested in. They do a lot of satellite remote sensing of vegetation. We did do experiments in this with prescribed vegetation, which is basically a monthly set climatology versus a fully prognostic vegetation. And the results in those in terms of these energetics weren't that different. They weren't as different as, say, just the reinitialization of soil moisture. It's not to say the vegetation dynamics aren't important at all. It's just they didn't seem to have as big an impact on the feedback to the atmosphere at this time. And whether or not that's just a shortcoming of the way that the dynamics are represented in the prognostic vegetation model, or the physics of the vegetation not really, feeding back as strongly, it's difficult to say. But yeah, no MP has a prognostic vegetation.
Any other questions? Take one more. Thank you, Dave.
Thanks.
And then on behalf of the organizing committee, we really appreciate Dave to step in a very short notice to replace the talk this morning that the colleague of ours that unfortunately did not make it. And so our next speaker is Alfonso Sanabori from the University of Calabria. And the title of his talk is Linking SST Representation to the Forecast of a Small Mediterranean Catchment's Hydrological Response to Extreme Precipitation.
It's right behind you.
Okay.
No.
These are okay. Just weeks of training. Yeah.
Yeah, it's side to side, and up is later.
Yeah.
There you go.
Okay, thank you very much. So, actually, this is sort of answer because I'm going to present for the first time all results about our analysis on how sea surface temperature representation can affect precipitation fields and then the hydrological response of small and very small Mediterranean catchments. But even if small can create some problem to the population. The main research questions are the ones you can see here. We wonder if resolution SST data can improve short range weather and hydrological forecasts. We are moving in forecast window of about 3 days or less. The SST fields representation is a level of uncertainty, and what is the extent of uncertainty of these SST fields with respect to other sources of uncertainty, especially initial and boundary conditions, and what are the implications for operational activities. If we assimilate sea surface temperature fields in the models, does it has any implications for operators of the agencies that work on the field? This kind of questions are addressed by several researchers, especially in Italy. Many research are going on concerning the Adriatic Sea that is on the east side of Italy, and the Ligurian Sea that is the northwestern side of Italy, and we present something related to the southern regions of Italy. Here we have Calabria, and you can see we already showed with some numerical experiments that show small changes in sea surface temperature can lead to different behavior of single events. For example, if we increase or decrease of 1/2 degree SST, we can have that the pressure minima tracks can go westward or northward with respect to the to this region. This kind of let's say classification is quite common from late summer to late autumn in the Mediterranean Sea. Here we have a clear example, almost they call it Medicane, with the Rhine hurricane happened, and it started in the sea from Sicily, between Sicily and Africa. And this behavior can lead to significantly different precipitation fields. You see that the main rainfall can happen if, on the sea or just close to the mountains in the middle of the. Of course, this affects a lot the hydrological response of the catchments and the impact to human activities. As a modeling system, we use the hydro. No need to say more words with respect to what they presented. I only stress that with our results, we made for a catchment in this region simulation with the analysis data for 3 years. We found very interesting, in our opinion, of course, results, but they are mainly relevant to long-range simulation because they are related to the fact that Gulf Hydro is able to distribute soil moisture, and then we found more soil moisture averagely in the fully coupled simulation with respect to the one-way couple, but this effect emerged after a period longer than 72 hours. So after some tests we used in our experiments with Hydro as a one-way couple. And what are these tests? They have been made on these two domains. This is the innermost one. You see also you see 10 kilometers for the outmost domain, 2 kilometers resolution for the innermost, and then for Gulf Hydro iris grid hydrologically, let's say, we have 200 meters. And sorry, I always press the wrong button. And we have the first test case about a convective event on August 12th of 2015, and then another test case about a stratiform, let's say, event that was longer, of course, and it happened the autumn after the first event. And what are the initial and boundary conditions that we consider? We consider all available real-time boundary conditions available. GFS, we are talking about 2015. So we, at that time, had GFS 0.5, 0.25, the ECMWF at about 16 kilometer resolution. And then as reference, we also used ERA interim data. Then with this forcing data, we replaced sea surface temperature fields with the high resolution sea surface temperature from Ifremer CERSA from France. And we made our comparisons. And for that, we also considered the uncertainty declared by people from this institute about the SST fields. The first events, very quickly, typical cutoff in the central Mediterranean. We have two low minimum pressures here in southern Italy and in all the Atlantic Ocean near the coast of France and Spain. And warm water was flowing from the African side. And then we had a cyclonic. Sorry, yeah. We have rainfall concentrated mainly in the very southern regions of the region. On the ground, we had essentially only one station of the regional monitoring network involved. It's Corrigiano gauge, where we had more than 220 millimeters in 12 hours, and especially 160 millimeters in 12 hours. And this created some problem that actually were especially hydraulic problems, because we have this creek, that is the Stitrea Creek. You see that it goes straight through the sea. Then they decided to build this village for tourists, and they moved the river. And what happened? The network doesn't forgive sometimes. So yeah, the embankment that was broken, and on the other was flooded. That was happened. Anyway, the precipitation is relevant because 160 millimeters in 50 hours is not light precipitation. What we did with our experiment? We considered the original fields of sea surface temperature, and then we considered the high resolution fields and their standard deviation. You can see from the differences between these fields and the high resolution fields that generally there is not a big difference. We have for GFS, that usually GFS is warmer in the Tyrrhenian Sea, but most important is the Ionian Sea. And we have some comparisons. I go very quickly. We have this national radar mosaic that confirms that in Calabria we have only one relevant event close to Corigliano rain gauge station and something else over the sea. We have for each of the slides you are going to see a control run precipitation field, SST assimilated precipitation field, and the differences. This is for GFS 0.5. You see that there is averagely more precipitation in the domain with SST assimilation, but not always. This is GFS 0.25. This is ECMWF, and this is entry. From the sequence, you can see that most important, more than SST boundary condition, as expected, I would say, it's important the input from the global model. In fact, you can see that precipitation goes northward from slide to slide, let's say. And at the end, with the air intake and the SST assimilation, we find that the rainfall peak in the Corigliano rain station is okay. Actually, you see it's very almost chaotic representation. So I don't know if it is here by chance or it's okay. Anyway, this is the best simulation, the best result. And anyway, as you can see from the scholar, we are at about 150 millimeters. Instead, from the world simulation here, we found more than 200 millimeters. A particular that I would like to stress, we initialized our model the day before at midnight. So we have to wait more than 24 hours before the main precipitation event happens. This is because we wanted to let the model system to have coherent atmospheric fields with respect to the new sea surface temperature field that we forced in the model. This is a slide related to the differences between high resolution SST plus standard deviation and high resolution SST minus standard deviation. That is, does the uncertainty in high resolution SST fields have any effect? Actually, it looks like it has some small effect. With the SST plus sigma, we still have this peak here, and with minus sigma, we have not anymore. And let's go on the rain gauge of Corigliano, that is the one that was affected by the event. You can see that when we have peaks far from, not close, let's say 20 kilometers far from the main rain gauge, from the rain gauge of Corigliano, we have that in Corigliano we almost have no rainfall. This happens for GFS, a little bit better for ECMWF, but it's not good. Even in the best case, that is the air intake with assimilated sea surface temperature, we have in Corigliano, more or less half the value of the observed precipitation. This is the evolution of the column integrated water vapor. We choose to show era interim and era interim with SST assimilated from the midnight of August 12th, that is a couple of hours before the event started, then at 6, when the event already started, at midday. And you can see that we have some more water in the air with the SST plus standard deviation, but the timing is more or less the same. There is not speed up of the process forced, for example, by warmer sea surface temperature. This is a series of hourly average water vapor flux moving through this transect. So we have from midnight of 12 to 12 o'clock of 12, how much water moved from the sea to the coast. This doesn't mean, of course, that all the water becomes land, but we see that the behavior is all more or less correct. We have at the end an anticipated behavior of the era interim simulation, and quite sarcastically, most of the time, highest values are given by era SST minus standard deviation. So at the end, the results concerning the hydrological analysis, you see that Citra Creek is very small, 11 square kilometers, so it's a big challenge for forecast. And you can see, of course, that if the model is able, sorry, colors are a little bit changed, but you can understand the same. We have a big flow, very simple hydrograph. If we have rainfall over Corigliano stations and near the Citra Creek with era SST, and no rainfall, not runoff if we have no rainfall close. The hydrometric coefficient, that is the contribution, let's say, of the unitary contribution of the catchment to the runoff, is about 2 cubic meters per kilometer. That is a little bit low for this region. We would have expected, besides the underestimation of precipitation, we would have expected higher values. We are just in these days trying to reproduce the discharge in this area according to some observations that have been made just after the flood. So we are confident that we can somehow compare our discharge with the, let's say, observed one. Okay, just a very small outlook to data simulation analysis. Sorry, data simulation. Yeah. The main impact of that simulation is that it increases rainfall in the area. With data simulation plus SST, we have something not in Corigliano that is here, but something northward. Anyway, the main events for roof happens here, where actually you can see these white points. This means that it didn't rain almost at all. We have just some rain here. Anyway, what are the messages from this from the first simulation? SST fields, in average, had not very high differences. Concerning spatial analysis, SST fields was able to improve era interim precipitation fields, but of course, GSM's forcing is more relevant than SST representation. About the timing of the forecast, this is always well, because the events start at the right time. Good time also for the hydrological forecast, but problems with the peak flow, even with the best forecast. Rapidly to the second event, it's something similar in the sense, I mean that we still again have a cutoff pressures, and, but in this way, in these days, we have the warm winds from south. In these days, we had more persistent event that was 3-4 days long. What happened? The whole Ionian coast of Calabria, this is the Ionian Sea, let's say. The whole eastern Ionian coast of Calabria in the south was affected by this event. We have up to almost 400 millimeters in 24 hours and about 700 millimeters here in 3 days. These are the damages that we made, especially to the railway near to the sea. Again, the same analysis as before. In this case, we have that high resolution SST is much warmer than SST provided by the models. And what happens? Here we have, this is the observed from the radar field. Maybe it's important to observe that the highest precipitation is here, that is just below the extreme south of the region. That should be here. We see that with the control run, we only focus on ECMWF and Erenteri now, not GFS. We see that the control arm reproduces the spatial patterns better than SST, the run with the SST simulation. We can see it clearly from the differences. Control run peak is western, on the west with respect to the SST simulation, and observation according to radar should be here. This happens also with the ERA interim. You see peak of SST simulation, peak of control run, observations. And analysis for SST plus sigma and SST minus sigma, that is standard deviation, are consistent. I mean, we have here the peak precipitation with the SST minus standard deviation, here SST, and here SST plus standard deviation. But you see that the differences are very small. Interesting is the analysis of the statistics about the evolution of the process. We have the most interesting figure, in my opinion, is this. The green line is ECMWF. The gray line, hidden a little bit by the others, is the gray line, and it works very well. Also, at the end of the forecasting period. Instead, if we consider ERA interim, it is quite good for the whole period, and we have that ERA interim precipitation finishes in a current way with respect to observation. But if we assimilate high resolution sea surface temperature to ERA interim, we have that the precipitation lasts a little bit longer. This analysis was made on this subdomain, let's say. So we consider only terrain, of course, not also the sea. These comments can be quantified with the Nash-Sutcliffe coefficient, that is maybe the most beloved coefficient from hydrologists. And you see that the value with the ECMWF with the SST is high with respect to the other values. These are the integrated water vapor fields from ECMWF and ECMWF SST. You can see that the water the area with the high water vapor meets the coast later with in ECMWF with the SST with respect to ECMWF. This is even more evident considering the flux, water flux through this transect. We have that ECMWF flux becomes quite constant. Instead, with the SST data simulation, we have a reduction and then up again. And this, according to rainfall analysis, it should be what really happened. What about runoff? We present here results about two catchments, the Ancinale and the Bonamico. For these catchments, we have not yet observed a discharge, but it's a better situation than before because we have hydrometric levels. So this is also something we are going to do in these days. We are going to reconstruct discharge by means of the HEC-class software, so that we perform the hydrodynamic simulation. We are taking measurements about the shape of the section of the rivers. And anyway, I would like to show you that about accumulated rainfall in this area. We have a rain gauge here. In this place, we see that ECMWF forecasts are very good, both with the SST simulation and not. You see that with the SST simulation, we have a shift of the peak flows, especially on the second event. We have two main events. This is more clear from this other section, because this is the Spagola, the smallest catchment, and this is Rexona, the biggest one. And we have that peak flow is a little bit with a little better tack with the ECMWF SST. And similar thing is for the Bonamico catchment, where anyway we had an underestimation of precipitation with respect to observation. But you see that there is some effect also of course, for discharge, and the trend of increasing discharge is well reproduced by the model. So, from this point of view, and also almost at the end of the presentation, the main findings of this analysis are that, according to other information, in all cases, high resolution SST fields worsen rainfall field representation. But the added value is that high resolution SST fields improve ECM WF timing and worsen a little bit error interval simulations. Hydrological forecasts are reflected, the rainfall performances are reflected in the hydrological models. Last observation, last comment, let's say, like a discussion. What are the effects on the operational activity? In the revision of the regional directive of the meteorological warning system in Calabria, the alert areas are going to increase from 6 to 8. What would have been happened with SST assimilation in these two events, considering both either 6 or 8 areas? If we consider the event of August 12, and we consider, for example, ECMWF with data simulation, we had a great advantage that we, with 6 areas, we would have alerted all this area. With 8 areas, maybe we would have alerted only this one, but not too much this one. We have some rainfall, but not too much. With the SST, we have also more rainfall here, so we would have alerted probably also this side with we have a yellow, orange, and red light. We would probably we would have used red light also for this area. Let's go on. Can you please move forward? This way. For the end of November 2015, the main advantage is not about the spatial pattern of the rainfall reproduction, but as we have seen, is in the timing. So this doesn't matter. This the zones to be alerted. Please, because it doesn't work anymore. Yeah. Our conclusions, we see that high resolution SST can improve short-range weather and hydrological forecasts. Some benefits of operational use are already evident, even though we are going to details, maybe analyzing more situations. But we see that science and goes on, and opportunities for modelers goes on, because since 2016, for example, we have 9 kilometer resolution in CMWF, so we have to check again what's the behavior with the operational forecast. Anyway, Wolf hydro modeling system can be operationally used also for southern Italy for gen weather and hydrology forecasts. Anyway, the step forward probably would be that coupled ocean atmospheric modeling would provide updated SST fields in a continuous way, so that the SST patterns can be better represented, especially coastal SST. And the last one, sorry, is that what we are looking forward is for fully coupled ocean and atmosphere modeling system that can be used also operationally. And it's for this that we have prepared the proposal for creating a network of researchers and the users about of these models, but we talk about this later. Okay, thank you. So.
Just wanted to ask, you use SST from Meteo France, you mean? This is the analysis, SST from satellite, is an objective analysis from Meteo France?
Yes.
I advise you to use now the Siemens new SST analysis, which is also done by Meteo France, but in an advanced way. And one question is, do you use daily and night SST, or you have only one field?
We use only one day field.
And so what is that one day field, since we have two passes, one that is night and the other is day?
Yeah, we use in the within the proof options, we use an option that allows to, given the mean the field to, I don't remember the name of the option for this option, but SST update allows to consider different values of the SST field during the day. We found from the IFRANA website only one day map. So
I think it's problematic because daily cycle in the Mediterranean
is very
high.
yeah. This
And
subset,
especially, you know, if you use daytime SST, you have strong surface millimeter layer of SST, so you don't have the real SST that is interacting with the atmosphere. Maybe you think that is foundation SST, the one that is most important. I mean, there are different.
yeah, but this is a good point because
you're looking at very much detail of the response, so it looks very strange that with high resolution SST you decrease the scale.
maybe one explanation could be that the SST fields are not fully correct with the behavior of the atmospheric
Yeah,
Maybe this-
we found that the radiation fluxes are not compatible with the same. Because of course, your atmospheric model will have its own SST fields, which would give a feedback into the radiation fields. So it's not, I think there would be some incompatibilities.
Oh, but you run WRF, you run WRF with the SST, you impose from Ethernet, right?
Yes, and this is
Okay, so then the fluxes there are whatever the model has with respect to that SST.
But
Will not be consistent maybe with the large scale.
which remains constant, yeah.
And it remains constant during the day. I mean, we found a huge difference in the ocean response when you use a daily cycle in the SST, if you impose the SST. So, I mean, I think that this is, yeah, I don't know, but it should be
Yeah,
changed.
I agree with Nadia, so we found very similar kind of sensitivity with compared to the ocean circulation model. So we found that especially convective response to diurnal cycle is a skin layer SST that Nadia was talking about. So usually when you use the satellite analyze, those are like the bulk SST, not true skin SST. So at least in the atmosphere, in terms of the heavy precipitation, there's quite a bit of sensitivity on that. But it's a very interesting topic. I think that's something that can be explored.
Yeah, it's something to be analyzed.
Did you consider to run the sensitivity experiments in ensemble or in the estimate the variations?
Yeah, we consider this, but it's a quite small computational effort. We are going managing to solve this problem from a technical point of view. But of course, it's another good part.
Yeah, just a related question. Do you have a sense of how your sensitivities compare to the kind of variability in rainfall that you get out of the ECMWF ensemble in the first place?
So can you?
So there will be spreading the precipitation out of the ECMWF or another ensemble. So how does that spread compared to the kind of sensitivity that you don't see?
You say that it would be good to make this kind of comparison, or you ask if I...
Yes.
Yes, of course. Yes, this is mainly a deterministic analysis. We consider the high resolution forecast in a deterministic way, and we just give a look to what happens. For example, I'm really curious if in the precipitation field of the convective event, the fact that we matched the precipitation on that rain gauge in a so restricted area is something that is given to the improvement of the initial and boundary conditions, or is something that just by chance. We should test with other elements that we have in this area.
Okay, all right, let's take some.
Thank you.
Okay, before we move to the next talk, I would like to the speakers during the break, please see either Louis or Carlos to load the new talk to the computer. Okay. Next speaker is Pedro Miranda from University of Lisbon. And then the title of this talk is Improving Water Simulation of Coastal Storms with a Better Water Vapor Initial Filter from INSAR Interferometry.
Thank you very much. Thank you for the invitation. Well, I've not been doing anything with fancy coupled hydro models. So instead, I'm going to show you something I've been doing in Lisbon for about a year now, which is to try new data sources from genetic information. Okay, most of my collaborators in this study are geologists. Only a couple of us are meteorologists. And what we are doing is to try to, for the first time, I guess, use these INSAR fields into methodological problems. No, it doesn't work. Can you move on? Okay. So, okay. So, we all know that coastal storms can be extreme, of course, because they have a lot of water vapor and a lot of mesoscale forcing, mostly topography, but other heterogeneities also come into play. In many cases, a model such as WATCH should be able to produce those storms, at least at high resolution. But of course, we have a problem to get the right initial state to get it. What I'm going to show you is to use a new data source, which is to use precipitable water vapor maps made by Sentinel-1 data and also by GNSS, and to assimilate those maps into WATCH using the 3D VAR scheme. Can you respond, please? Okay. GNSS data, it's GPS data, has been used for some time now into hydrological analysis. It produces kind of 50 kilometer resolution data. It can be updated very frequently, maybe up to 1 minute. What we are going to use here is a new data source which is in many ways very similar to the kind of data you get from GNSS. But the difference is that it is very high resolution, maybe 20 meters in raw form. And at the same time, this resolution is real in a way, because when you get a GPS network, the distance between the stations does not give you the real resolution of the data. It is coarser than that, because of these inverted cones that the GPS sees. We have at this time, these images, these SAR images are available every 6 days. Every 6 days we have 2 images at this moment. And from these images we can produce differential images by interferometry, which can be interpreted as water vapor fields. Okay, there's a lot of text there. So the case study I'm going to show you is a very peculiar storm, which happened in southern Spain, in Madeira, near Almeria. This was a very intense storm, which it happened a couple of years ago. It led to a significant flash flood, but it has a special setting, because it in fact consists of 2 storms, about 12 hours apart. The first one on the evening of the 6th of September, and the second one about 12 hours later, on the morning of the 7th of September. Exactly the same place. In fact, the flash storm took place in the second event, not in the first one. Although precipitation was very intense also in the first one. Can we move on? So, this storm was not forecasted by operational models. It was not a resolution problem, because we tried 3 kilometer resolution simulation of the 2 events, and we got essentially no rain in place. So, the other good thing about this, and in fact this is why it was selected, we only have these images every 6 days. It just happened that we had one Sentinel passage just 6 hours before the first storm and 6 hours before the second storm. So we were in an excellent place to test if this would work. Okay? Can you move on, please? So this is a movie. It's a bit big. You have to click somewhere for it to run, I think. You can go to the middle of it. It will take too long. So this is the kind of effects. There are some people died, maybe 4 guys, and there was a lot of destruction in the city, because, of course, it's a very narrow roads. There are slopes, of course, and it produced a significant impact. You can't just get out of it. Just to give you a feeling, this is a big flash flood. Okay, no information here, so. Okay, so the questions I'm trying to answer this is, can you improve this using GNSS data? GNSS data gives you precipitable water vapor at very high time resolution, but not so good spatial resolution. It was used in the analysis in some way, but not near the effect. And of course, the second thing is, can we do better with INSAR? And why, if we can, and we can, why can we do that? What happens in the model, at the simulation time, that changes the fields and what does give what's necessary to produce the song? Okay. So this is just to remind you what the SAR product, this is the synthetic aperture radar system. In fact, what it does, you have a radar, flying radar, and the radar is not so very big, so you know the resolution of radar depends on the size of the antenna. The size of the satellite is not so big, but what we do is we use different positions along the path, and we combine them to produce a single image. This is why it is called a synthetic aperture. So it behaves as a very big, say, hundreds of kilometers antenna, and that's how it gets this very high resolution in the ground, which is, in fact, depends on the direction. It is 5 meters in one direction, 20 meters in the other direction for the raw data. Okay, we can move on. So we can, when we have two images which are produced at different places, in this case they are 6 days apart. So we have one image and another one 6 days later. These two images are in the same view, but of course there are some differences, some slight differences in the position of the satellite because of perturbations in the atmosphere and many other things. And if we combine the two images in this what's called the interferogram, we have a combined signal, the interferogram. And if you look at the phase of this signal, this phi, it is associated with the differences in these two rays, the differences inside these two rays. So from that phase difference, we can infer a change in the length, which is the reason why this system was made. This is made for geodetic analysis, so it is used for example, for seismological after changes, for changes in land, whatever you look at. But if the land is quiet, which is generally the case in 6 days, unless there was an earthquake or something like that, or a landslide, if it didn't happen, then the only thing that changes this apparent change in path is the fact that it's the same path, but in fact it took a longer time to go through because of the composition of the atmosphere. So we can get this phase delay as a proxy for water vapor integrated along the path. So it's called the slant water vapor, and from there we can compute the precipitable water vapor. Okay? So this is just how we do it. There's a kind of empirical analysis. This is the initial map, and this is a water vapor map you get when you do the empirical corrections, and you get off the information you get in the ground. So you use your terrain model, and from that you can get a water vapor map. If you assume there was no land movement. Okay. Each SAR image is something like this rectangle here. So what these guys have been doing in Lisbon is to get a way of stitching these maps to produce a single passage map. So from these 5 images, you can get one single image. In this case, in the interferogram, this is interferogrammetric image, and this is a perturbation of water, precipitable water vapor. It's integrated water vapor in the column. Okay. If you go to, this is interferometry. Now, if you look at water vapor in the initial stage, and we've used GPS data to calibrate that. We need GPS because GPS gives you not normally of PWV itself. You can get direct PWV from GPS, absolute PWV. Then use GNSS to calibrate, and we'll get the water vapor at the final date. That's how it works. Okay, we have tested it in a number of places. So this is how we are going to do this analysis in this case, this event. This is the UTC time scale. So we had these two storms. We are going to use an analysis, in fact, a forecast that was produced. We are going to use, in this case, the forecast starting at 12 and starting at 0. But then at 18 and at 6, we are going to do an assimilation where you're changing the fields that were forecasted here, and from these fields we assimilate PWV. And then we do 12-hour forecast from there. We do another simulation at 6 a.m., which is these two dates are the passages of where we have the INSAR data. So we have INSAR data at 18 and at 6. Okay. Then we do 3 simulations. So I'm going to show you comparisons of 3 simulations. First one is the control simulation, where we just use the simulation from 12 to 0. That means simulation with boundary conditions from a global model without any specific data, extra data. On the second case, we'll assimilate the GNSS network in Iberia. I'll show you what it is, except for a few stations which you keep out for calibration. And in the final run, we'll do INSAR simulation at these times. But both GNSS and INSAR are doing at the same time, so we are just doing a single shot at one time. Okay, I have to move result. Okay, this is Iberia. So you'll see these triangles are the GNSS network that we are simulating. There are a lot of them, and these stars are an international, European network, which is the same kind of stuff, but we are keeping them aside to get an independent set for calibration, for validation, in fact, in the end, for validation of PWV. This is the image in the ascending orbit. The Adra is in the center of this circle here. And so this is, in fact, this is now the PWV, which was computed from that image after this processing of the INSAR data. And this is the image 12 hours later of the descending orbit. So they are different geometries. You cannot use the two orbits to produce the interferogram. So that's why you need to go 6 days before to get a similar view. But they have both have some footprint in R. Okay, so we are using 130 stations, and we are keeping 35 apart for the validation. Okay, this is what happens to the model. So on the top, I have the first event. In fact, at this time, in this case, I'm looking at a simulation time. It means this one is at 6 p.m. at 6 a.m. in the next day. So the left figures correspond to the GNSS case. In this case, I'm just showing anomalies, so the control is out. So this is differences to control. So in the first case, this is what GNSS does to the data. It produces an anomaly of water vapor mostly centered in this region, whereas with INSAR we get a much bigger anomaly of water vapor. This is the colors, and with a lot of signature in other. And at the same time, of course, the simulation system does not change only water vapor. I'm simulating PWV, but I'm looking at specific humidity in this case. in the model. But it also changes temperature and wind. And in this case, there is a significant change in temperature, but about 1 degree in the center of Iberia. In the second event, the anomaly is quite smaller, as you can see in both cases. Well, in this case, about the same. It's a bit smaller in this case, and they are not so different. There's not such a big difference between GNSS and INSAR. Although the INSAR field is a bit more intense in terms of humidity. I'm looking at a level in the model which is about in the boundary layer. It's a fourth level in the model. Just to give you an idea of the kind of air that's going to produce a storm. Okay. So this is a cross section across Adra. This is the north-south cross section there, and you'll see that in the GNSS simulation, the anomaly is very difficult to see. In these colors, almost, well, it's in there. It's maybe 0.6 or something like that. Whereas in INSAR, you have a big anomaly. Adra is here at the coast, okay, but the maximum anomaly is slightly above the surface. And you also see these anomalies in temperature which go to 1 degree in places. In the second event, at the surface, you didn't get so much of an anomaly, but you get a big anomaly up in the air, in fact. But this is inside Iberia. What matters most is what's happening here. And you'll see that in this case, you won't see much difference between GNSS and INSAR. They both produce a positive humidity anomaly in the coast. Okay. This is also at the simulation time. What happens to the Cape field? And you'll see that you have different situations. In the first event, you get really big values of Cape. Kind of Cape you could get in the very deep convective systems. So you could get tornadoes with this kind of Cape if the shear was right. But and this kind of Cape happens mostly in the INSAR case. In the GNSS case, you just have an increase in Cape, but not so big values. But they are above 1,000, so they are quite big anyway. I should remind you that the INSAR data is confined to the continent, because what the interferogram sees is changes. Because to produce the interferogram, you need to have features in the ground which are fixed, because that's what the radar is looking at. On the ocean, you just get noise. So you are just putting data inland. However, the WRF 3D VAR system will somehow expand it a little bit over the ocean in the nearby region at the simulation time. And then it will evolve by on its own. Okay, so we have some anomalies. Well, these are not anomalies, are values. So, because I'm here showing control, GNSS and INSAR, and you'll see that we have changes both inland and over the ocean because of this extrapolation, which is done by the 3D VAR system. On the second event, you also get a bit an enhancement of Cape in some places, but not dramatic. So there's not a big change. However, the big flood was in the second event. Okay. So to try to understand that, we are now looking at not at estimation time, but just in the hour where the storm started. So the starting lasted slightly less than an hour, and we are looking at the initial at the hour. So this is at 21. This is at 10. So the start was from 21 to 2, and from 10 to 11. And here I will show you two things. Again, Cape, the same field, but at the same time, I'm showing you the streamlines in the the same model level I've shown you before. This is at about 400 meters. So you'll see that the big difference here, there is, of course, I've shown you the differences in K, but there is also a big difference in the circulation. You get at destination time a lot of convergence from air coming from the ocean into the land here, whereas in both the control run and in the GNSS run, the circulation is essentially parallel to the coast here. So this change in circulation is very relevant. And the same happens, although not as much, in the second event. You also get a kind of change in the circulation, and it is bringing air from this region here, where you've got maybe 1600 in Cape. This is a different hour, so it's a different Cape. This is just before the storm. So we have this tone of high Cape, which is at this level here, maybe 1600, and we have a circulation bringing this air into the continent, and we have a kind of convergence here. Whereas in these other cases, we don't have a convergence region near the mountains. Okay, and this is just the INSAR simulation now. The others didn't have any signal, in fact, so you wouldn't see anything. And you'll see that this is now, during each of the storms, 2100 is every 20 minutes. So the storm lasts maybe half an hour in each case. So you get these very deep convective systems. There are other systems in the mountains much far away, but there are no cities there, so no one cares about that. And this, of course, rain coming here will then run off to other areas very near the coast. And so you have these systems which last for some time. And if you look at the second event, this convective system is much stronger, and it lasts slightly more, in fact, in the second event. So you get really the right kind of convergence near the slope, which produces the flood. Okay, so this is now a tentative to do a validation of our approach, looking not at precipitation, but looking at the forecast of PWV. And to do that, we are now using these 35 GNSS stations which were not assimilated. They were not used for anything else here. And we have now we are now looking at two different things. One of them is the root mean square error, and the other is the skill score. The skill score gives you the improvement from the control. So we have the control, we have GNSS simulation, which is the blue line, and then we have the INSAR simulation. So we have a reduction in the root mean square error. In both, this is one simulation, this is the other one. And we have an increase in skill score by 75% in the beginning, and it's about 0 for maybe 8 hours. So we have a better forecast of water vapor. This is for the full domain in this case, during 6 to 8 hours in each of these simulations. Okay? This is now a validation in just one point. This is the other rain gauge. So we have this green line is the rain gauge, and this red curve is the INSAR simulation, and the black one is the control with snow rain, and this blue line is the GNSS simulation. So we do get a bigger pulse of rain in the second event, not as big as observed, but it is in the right timing and in the right place. Okay? I guess this is my final picture. So this is now a comparison with the data from the radar in Almeria. So this is 1 hour accumulated rain. And so I have here the control, the GNSS simulation, INSAR simulation, and the radar. Of course, the radar, in fact, the radar produces a lot less rain than observed. So radar is a very processed data set, of course, but you do get these 2 bits of rain, which we get in our simulations. If you go elsewhere, you maybe think that we are producing too much rain compared to the radar. I'm not so sure. It depends. We would have to look at this at other rain gauges. At least in the rain gauge we are looking at, it's okay. Okay. So this is it. So what I've shown you is that it is possible to simulate this new data set of the Sentinel images using this INSAR approach. And in some cases, at least, it seems to improve the behavior of forecasts of severe precipitation. If you look at, I didn't tell you many details about what we have done. These images in INSAR, they are about 20 by 5 meters, but to simulate them into WRF, we had to aggregate them to about 15 kilometers. So it's not so high resolution as you'd imagine, because we couldn't simulate high resolution because the 3D VAR system requires the data to be uncorrelated, and if you do very high resolution, they will be more correlated. So this is what we have tried different ways in kind of trial and error. This is what seems to work okay. This is not so much higher than the distance between the GPS stations. However, the problem is that these GPS stations are very correlated because they have these inverted cones. They look above. They have a system of acquisition which allows the satellite to tell you from very low angles. So this means they have a lot of superposition. So they are much coarser than they look when you look at the map. So we could probably, as it is operated now, GNSS data does not give you the kind of detail you would need for this storm. Although it improves something, it does not give you. Maybe if you would acquire data a different way, they could be used. Well, I've told you that. It seems that the impact of this input of data, in fact, we have done other attempts, not with such a big storm, because also it's going to be a big storm just after the image. But it seems that the impact of this data lasts for 6 to 8 hours. So you would need to have frequent data. Of course, at this time, we only have 1 image every 6 days. So we are not at the point of putting this into operation. The final thing I should tell you is that I've just emphasized that we are only simulating integrated humidity, but the model does some apparently clever things to also perturb wind and temperature. I'm not sure if they will be as clever in all cases. That's the problem. But these changes seem to be relevant to get the storm going. Okay, this is it. Thank you.
Nice presentation. Thank you. Can you check the reason that the model failed to produce this event in the control line?
Well, our guess is that it has not enough humidity because we have very significant humidity anomalies in our simulated system.
You forced to work with CWF data, or?
Well, in fact, we tried both. It didn't produce in any case. So it seems that in this case, and in fact, it was not just WRF, because the Spanish system does not use WRF for forecasting. They use the new Ireland, I think, which is called Harmony or something like that, which is a different system. And they didn't get, but of course they were getting initial state from the same way. So it will be the same. So in this case, it seems that initial state is critical. Of course, not all cases are equal. But the point here is that this new data seems to be usually indices. So this has been submitted, so we have no input yet.
Yes, I allow myself. So, looking at the second event, maybe there is too much humidity in the northeastern side with respect to other observations.
This is precipitation, not humidity.
Yes, but I mean there is too.
Yeah. I would say that radar data should be. This is radar. Radar data is more qualitative than quantitative, I think. You should mostly look at the pattern and not so much to the values, because the pattern is not so bad. You have this is observation, so the pattern is not so bad. Of course, the values seem to be much lower in the radar, but if you look at the stations, radar just gives you 20 millimeters, and you got an observation of 60. So maybe the radar is just underestimating precipitation. So.
Any other question? I've got one for you. So you mentioned that you use a 3D bar system to assimilate the seed quantity. How do you distribute the moisture vertically?
Well, that's what 3D DA does.
Yeah, do you know?
We just computed. Well, I've shown you what it did. In fact, what we had to do is, of course, to prepare these covariance error maps, which we did with a number of a few months of simulations to get the model running, just to initialize these 3D covariance error fields, which is needed to initialize the 3D bar system. But then the 3D bar system just does what it does. In fact, what it did was to put the humidity mostly at low levels. But it affects full column. It is mostly at low levels. So, although it's not an exploration, so the maximum is not at the surface in this case. But it's something that's already built into work.
So do you think that there is a sensitivity in how you distribute the vertical moisture in terms of the resulting convection?
Yeah, sure, but in fact, because we only had these integrated fields, we didn't have any reason to prescribe otherwise. You could, of course, assimilate specific humidity if you knew what it was, but then it would be a different problem. We just had these integrated fields.
So the last talk of this morning's session is from Xiaowu, and the title of this talk is the hydrological response for the FC River Basin to the stream rainfall event. And Xiaowu is from the Coastal Carolina University.
Okay, so good morning, everybody. Next, I will be talking about actually an application of the Wolf hydro model to simulate the response of East Coast river basin to extreme rainfall event. So the main person who did this work is a graduate student, Mr. John. Okay, so this rainfall event occurred from October 1st to the 5th in 2015. It's a 4-day period. And this is a 1,000-year event because if we look at occurrence intervals, in many locations in South Carolina, the total rainfall event total rainfall amount during these 4 days exceeded 500 year or 1,000 year return period. For this event, we observed the two interesting points. The first is a 1,000-year event or 500-year event didn't cause the river's response of the same recurrence intervals. So the river's response to this extreme rainfall is quite mild. Because we couldn't find the data about the river discharge return period, so we did our own analysis. So we calculated this return period of most of the South Carolina River discharge using historical data, and we found the river discharge return period only exceeded about between 20 to 50 years levels. So why did this 1,000-year rainfall cause only 20 to 50 years discharge? That's what we want to figure out. Another point is the response of the rivers is quite delayed. So if you look at this black line is this rain rate, precipitation rate. And here is this river discharge. So we can see this rainfall reached its peak around October the 2nd. But this river's discharge reached its maximum only almost more than a week later. So we have some emergency managers talking with us about this and say, after the rainfall ended, they thought, okay, the storm passed. Only to find after a week, this flooding and discharge came to its maximum, to call them off guard. So it's interesting to figure out why we have this kind of pattern of the river respond to such a big rainfall. Because we only have some discharge gauge data from USGS. So due to the limited data availability, we decided to use the model. So we use the warp hydro model to simulate this, how this river responds to this rainfall. So we selected a typical basin. This is a Wakama River basin is a typical East Coast river basin. And it's low-lying. And land use, the land type is mostly a wetland with very high infiltration rate. So we divided this whole basin into 5 smaller sub-basins. The basic hydrological processes. So we know the rainfall, the source, and the sink could include evaporation and transpiration and some surface-derived surface runoff, the quick runoff, and then we have this underground flows, and we have some water storage. So we use the warp hydro model trying to focus on answering several of the questions. So what are the balance during this rainfall event? Which is the dominant process? Is it the direct surface runoff or the slow underground runoff? So why we have this discharge lagging behind the rainfall? The role of the land surface type. So the warp hydro model, as Dr. Gorgeous has given us a very good introduction of World Hydro System. So we know in the history of hydrological model development, we have had the black box models, basically statistical regression. And then we had these conceptual models called the gray box. And then in recent years, we started to have this physics-based models. So World Hydro is a distributed physics-based, but it has a unique underground module to describe the underground water flow processes. So it is so-called a bucket model to describe the underground. So we can imagine the water river, the river water from the rainfall that goes into the soil and then goes to underground. Then we describe this as going into a conceptual bucket. And then the water that goes into this bucket will flow out into river channels using an exponential relationship. And when the water goes out from this underground bucket, conceptual bucket, to the river channels, it's distributed evenly across the sub basins. Okay, so that's some of these basic processes in World Hydro. So the input, we all know the rainfall data is the key driving factor to drive a hydrological model. So for this simulation, we use the radar reflectivity derived precipitation rate data. Here is accumulated precipitation using this data type. And we did some validation. You can see this radar reflectivity derived rainfall and this rainfall data at USGS gauge stations, they agree very well. This gives us some confidence that we can use this radar derived rainfall data to drive the World Hydro model. Okay, that simulated hydrograph. So across this river basin, we have 4 USGS stations, and we have this measurement, discharge measurement. So again, this precipitation event only occurred in 4 days period, but we can see for the simulated and this measurement of this discharge lasted quite long. It's lasted into a month, more than a month's time. And we can see this simulated hydrograph doing pretty well with this measurement. Again, this gives us confidence, and we can use the simulation output to study this response from river to rainfall, and will help us to figure out what happened during this event. So we did a water analysis, water balance analysis. Here we are looking at this domain total of time accumulations of different processes. Except this green line you see here, that is the total rainfall storage in the soil and the soil moisture. So let's start with this rainfall. This blue line is the rainfall. Again, it's accumulation with time. You can see this is a quick rainfall event. And then it pretty much stopped here and become level, the accumulation become level. So it's the rainfall only is from here to here. if you look at this soil moisture storage, then we can see there is a quick response that a lot of this rainfall goes into the soil and becomes soil moisture. Here. But it stopped over here, I think because the soil got saturated, so started to decrease. The soil moisture started to decrease. When this happens, where did the soil water go? It actually goes into this conceptual bucket, underground bucket market. So we can see it here. This purple line is the bucket inflow. That is the rainwater that goes into the soil and then leaves the soil into underground. So this bucket in will increase slowly. It didn't act like the soil moisture. The response is rather slow. And even after the soil got saturated and started to decrease, the water keep entering this conceptual underground bucket. And this process will keep increasing, keep happening throughout this 30-day period. And when you have the water that goes into this conceptual bucket, and at the same time we have water that flow out of the conceptual bucket into the river channels. So that's this line, this blue line. And if we look at this evaporations, you have canopy evaporations, we have the land transpirations here. They are pretty steady. It's just a slow process. But one thing is striking is if we look at this direct surface runoff, this amount is tiny. So this direct surface runoff is this red line. It's a very, very small amount. So this tells us, according to this model simulation, most of the rain water enter the soil first with a quick response into the soil, and then flow from the soil into this underground bucket, underground flow, and then slowly release into river channels. But this direct surface runoff only played a very tiny role in this whole process. So this explains why such a 1,000-year rainfall event only cost between 20 to 50 years discharge level. And also this explains why we have such a big delay between this rainfall, big rainfall, and this discharge. The discharge maximum reached this maximum 7 days, almost 7 days after this rainfall event. So obviously, the key here is in this type of East Coast river basins. We have this land type, a lot of wetlands, forests. These land types have high infiltration rates. So that high infiltration must have played a critical role so that a lot of the rainfall, most of the rainfall can enter the soil as soil moisture instead of flowing in on the surface, becoming surface runoff in the river channels. So to test this idea, we ran some hypothetical experiments. So we say, what if all this land surface become impervious? so that no infiltration happens. We run the same simulation, then we see these dashed lines are this discharge if the land surface becomes impervious. So we can see this response at the whole USGS stations. So if we go back to our previous slide, here, we see we are looking at the same 4 USGS stations, but in this realistic simulation, you can see this response agree very well with this measurements, and the amount is about between 500 to 600 cubic meters per second. That's the discharge rate. And this agrees with measurement. But if we disable this high infiltration, then we see this discharge rate increase to 1,500, 3,500. That's almost 7 times larger than the realistic simulation and the actual measurements. So this gives us an idea about how this high infiltration land use played a role in this whole process. So before we use the work hydro model, we try to use some tools to analyze how this discharge, the measurement of the discharge can be separated as a quick flow and slow flow. So we have some statistical tools such as this local minimum method, one parameter method, digital filter, recursive digital filter. So before we use the model, we try to this kind of analysis. Then we found this different methods give us pretty different results. For example, in this case, we see this measured discharge is separated at mostly direct runoff, and then it's a constant phase flow, the slow runoff, which is obviously not correct in this situation. And then we have other methods giving very different results. In this case, most of this flow is separated as the phase flow, the slow runoff. And here is in the middle. But this highlights the need of using actual physics-based models such as the work hydro, because really the separation of this discharge into quick surface runoff and slow base flow runoff really should be done on storm by storm and case by case, basin by basin basis, using one method to try to if the storms, if the basins has a problem. That's all I have. And the main conclusion is this extreme rainfall didn't cause extreme river discharge, because the dominant process in this case is this slow underground flow that goes in the underground, then slowly released into river channels. Okay, any questions?
So it's an interesting result. I don't remember if you said it. Was this event preceded by a very dry period where soil moisture storage became very depleted, or it seems like you could have a very specific threshold-based behavior if your soils did become saturated in here and therefore couldn't take up this. In this event, were the antecedent soil conditions very dry, or was there some other situation that led up to them being able to pulling that much water, or is it just the subsurface in this region just that efficient at processing inflow?
We actually did a 1 year run, spin-up run before the start of the rainfall. And I think prior to this rainfall event, we have some other mild rainfall events before this. So probably making the soil saturated.
Vincent? And then Maria.
I guess I have a basic question about water hydro. So there's surface runoff, that's water that never enters the soil, I guess. And then there's this bucket at the bottom. Is there some intermediate process that allows water to move into the soil, into the soil and then to the river network without going to the bucket?
My understanding is in water hydro, the direct runoff is sometime when this rainfall is too heavy and the infiltration is not high, so some rainfall didn't get a chance to enter the soil. They will move horizontally above the surface and may become the direct runoff into the rivers.
And everything else that enters the soil.
And we also have the subsurface runoff.
Yeah. So this subsurface runoff was zero, or I didn't see?
The subsurface runoff in this case is combined with this underground runoff.
Okay, so you added it to the bucket.
There's a couple different things that can happen. So he's right, and you're right. The main two mechanisms are overland flow, never enters the soil, and then water which goes through the soil, drains out the bottom and bucket and gets discharged back into the stream. A third, more nuanced case is where we are using the lateral subsurface flow, as he mentioned, and that actually saturates the soil column and exfiltrates back to the surface.
It's added to the surface runoff.
And then it goes back to the surface runoff. So there's a few different pathways. What I think you're looking for is that direct link between the soil column, soil moisture, subsurface moisture content, and the river channel. That currently doesn't exist right now. So you don't have that two-way exchange between the river channel and the soil column. But those other pathways do.
So in this case, this surface runoff includes water that would exfiltrate.
Could have been.
Could. So that's interesting. So did you, just a substitute question, did you have to calibrate the parameters of that bucket? Because since it's very conceptual.
Yes, we did, yeah. We actually calibrated this different parameters using some software package called automatic parameters estimation. Did some tuning.
Yeah, I mean, the previous question was already part of my question, so we also have experience that you need to calibrate a lot of these parameters of especially of the bucket model and so on, of the aquifer, let's say.
Yes.
So I think we are lacking adequate observational data to at least in some key pilot area to really see how much are we missing some of the feedbacks that David was actually talking about, and how much is the details of these subsurface modeling that we need to account.
Yeah,
So,
exactly.
yeah, what is the, can we plan in the future a good experiment in some basin that would finally critically quantify these parameters and show the most important ones? Because there are too many, and we know that some are correlated. So we need to discern which ones are the most important ones, and maybe even have a continuous monitoring system so that would continuously improve the representation of these parameters along the time.
Yes, I think the reason we have so many parameters and we have to train these parameters is because we don't know what exactly this underground aquifers look like. We don't have the survey data as well. And I believe in the future, if we have more of this data, we can more accurately, realistically represent this underground aquifers in the model, so we don't have to artificially twin these parameters.
Were you able to find any case of intervals, like from USGS, see what is the water table?
Water table.
Your groundwater level?
The only data we seem to be able to obtain from the USGS station is discharge, this stream flow data, and this in some places what have the rainfall and precipitation rate.
Because it would be interesting to see, for example, how many aquifers you have in that area, is they confine that filter, is they not confine that filter?
Yeah, that's,
so all these things are important.
That's a good point, because we haven't reached that stage of this work.
Yeah, and I feel also that maybe if you use a distributed hydrogeological model, then you might not find you might find different conclusions with a very simplified model. So I think it might be worth looking more into the hydrogeology and see how that propagates filtration structure.
Yes, yeah, that makes sense. So I don't know if the World Hydro model has any plans to replace this bucket, conceptual bucket model with more realistic physics-based.
Yeah, the folks in Germany and Garmisch have implemented a deeper two-dimensional groundwater model. It's an experimental branch of the code, but they've shown some very promising results in being able to get the two-way coupling between upper channels and subsurface structures in there. We have other partnership with another group with the School of Mines who's working on the park flow model, which is very computationally intensive 3D Richards equation-based model of the whole subsurface. And looking at that, I think the point, yeah, I mean, it will be good to have these representations, and at the point that the subsurface always comes back to the parameter estimation problem in subsurface. Lacking the data, we usually have just too much unconstrained uncertainty in estimating model behavior. So to Nadia's point, I don't think as we get to physics-based models, we're never going to reduce the number of parameters, but we have to find novel ways to constrain the parameter range.
Exactly.
So that we can do that.
And we need to have the observing system planned for doing that.
Yeah.
Because it's not so easy to get, yeah, exactly.
So you have some good points. So maybe tomorrow when we have the discussion, and this could be one of the action items that as a group definitely we try to get some back with them to kind of build an observation. Any other questions?
I just want to say thank you. I think you're the first person I've seen who's never run the model and never asked for any user support or help or anything.
Actually, we asked, the students asked.
Oh, you did? It must have been minor.
This is in contrast to the Italians, who ask a lot of advice to give
Okay, thank you.
Okay, so we're going to take a 15-minute break and move on to the next session. So we have the break in the restaurant. Upstairs.